Hello everyone, this is Key. I'm currently a researcher at Visa Research. Today I'll be presenting our work, Learning Semantic Programming Embeddings with Graph Interval Neural Network. This work is led by Yu, a PhD student at Nanjing University. As Yu is busy with his defense and graduation in general, I'm giving this talk on his behalf. Our goal of this work is to develop a general, effective neural network that learns precise semantic embeddings of source code. Here by semantic embeddings of source code, we mean continuous vector representations of programs. Ideally, our model should work across many client applications with respect to the different learning objectives. Let's start with a brief summary of the related work. Initially, program representations are learned through token sequences so that the natural language models can be readily applied. Later, program representations are learned through abstract syntax trees for the benefit of incorporating the structural information programs exhibit. A few years ago, graph neural networks are introduced to learn program representations from their graph format. The issues with the prior work is that the indiscriminate program representation, meaning most of the existing works do not take into account the unique properties programs possess. For example, when programs are reduced into sequence of tokens, they are perceived by the models to be sentences or words. When learning from program graphs, models treat them the same way as molecules or social networks or any other graph data. Some works consider incorporating semantic program properties in a limited fashion, such as adding data flow edges into abstract syntax trees, but those techniques are ad hoc. There is no systematic approach on which edges to add for different graphs and downstream tasks. Unlike the prior work, which focused on program representations and the models per se, our insight is to improve the capability of existing models by learning from abstractions of programs. In particular, we design a method to decompose the whole learning problem into subproblems, and more importantly, focus on subproblems of greater importance. So how do we realize our insight? First, we adopt the graph neural network as the base model due to their cutting-edge performance. We use the control flow graph as the input data. To enable fine-grained representation, we split nodes of basic blocks into multiple nodes of statements, each of which is represented as a token sequence. Now the most important part about the abstraction method. We abstract programs directly on their control flow graphs based on a special graph structure called interval. So what is an interval? Formally, an interval is the maximum single-entry subgraph with only one entry node, and all closed paths contain that entry node. What does an interval denote in a program? It is precisely the loops. The loop headers are the entry nodes, and all paths in the loop go through the loop header. Now we give the details of our interval-based abstraction method and how it helps graph neural networks to learn. We use this program as our running example. First, we construct the control flow graph of the program. Each node corresponds to the box marked with the same number in the program. Then we partition the graph into a set of disjoint intervals. We use different colors to signal the different intervals in the graph. The first principle we introduce is learning will only happen within an interval. In this case, it's the interval of node 3, 4, 5, and 6. As for the detail of the learning approach, we adopt the same message passing mechanism that empowers the standard graph neural network. Other intervals, which all consist of a single node, will be ignored at this stage. As you can see, models exclusively focus on the inner do-while loop at the current stage. After the learning converged within each interval, we now introduce the second principle, which is to combine the nodes within the same interval into a new node on the graph, aiming to expand the region of the learning target. In this case, nodes 3, 4, 5, and 6 are merged into node 8. Similarly, we reprocess the resultant graph into a new set of intervals. This time, we have the node 2, 7, 8 forming an interval, which now directs the learning. Since node 8 can be seen as a proxy of nodes 3, 4, 5, and 6, models look at the entire nested loop structure at the current stage. So by merging nodes into new intervals, models indeed focus on a different, larger part of the input program. Then we perform the merging operation again, which enables the model to learn from the whole program effectively. After the learning converges on the entire graph, we need to recover the original program representation. Now we introduce the last principle, which is to split the combined interval node back to the individual node that were in the same interval. When models learn from the same interval the second time around, they can take into account the representation of the entire graph they have learned earlier due to the merging operations, a capability they do not have before when dealing with this interval last time. We continue to apply the split operation until the original graph is recovered. This entire process can be repeated multiple times to allow sufficient information exchange. Compared to the standard graph neural networks, our abstraction-based learning approach provides the following advantages. First, it decomposes a whole program into a hierarchy of loops to enable models to solve smaller and easier problems. Second, models can focus exclusively on loops, a vitally important program construct. Third, a well-known issue with graph neural network is learning from nodes that are far apart, since messages can get diluted as they are passed along the graph. With our abstraction method, models always deal with intervals that are small and the long-range dependencies are rare. We evaluate our approach in 3 learning tasks: predicting variable misuse, predicting method names, and detecting null pointer dereferencing. For variable misuse prediction, we use gated graph neural network and RNN sandwich as the baseline. We also curated a dataset out of ETH PY 150. Results show our model is more accurate than both baselines by a comfortable margin. We also examine how models perform when the size of graph increases. We split the test set into 10 partitions based on the size of the graphs. As shown in the figure, the sandwich model, which is the black line, learned with the abstraction method, is the most scalable models among all. In method name prediction, we compare our approach against sequence GNN on Java Small. In terms of accuracy, results again show our approach outperforms the baseline significantly. As for scalability, our approach, which is the red line, performs better as the size of graphs increases. Finally, in null pointer dereference detection, we compare against the graph neural network on 4 existing datasets proposed by the prior works. Results show our approach is more accurate than GNN significantly. Regarding scalability, our approach, the red line again, yields better performance than GNN when dealing with large graphs. We also deploy our model to catch bugs in the wild. On 20 highly starred Java projects on GitHub, our model detects 38 bugs out of 102 alarms compared to 34 bugs out of 129 alarms by Facebook Infer. Among the bugs we reported, 11 are fixed, and 12 are confirmed. To conclude, in this work, we present a novel approach to learning from abstraction of programs. Our interval-based abstraction method significantly improves graph neural networks' capability across 3 different tasks. For future work, we would like to apply our idea of abstractions for more models to more programming language tasks. That concludes my talk. Thank you very much for your attention. I'll be happy to take any questions that you may have.